Welcome to the course Computer Architecture. My name is Nachum Danzig. I teach at the Jerusalem Academic Center, Merkaz Academy Lev, the Lev Academic Center in Jerusalem, Israel. And we are in chapter 6 of the course, and we're discussing how to enhance the basic MIPS architecture so that it supports all the commands or other commands that are found in the MIPS instruction set, and theoretically how we would add any additional command that we might want to add to the architecture. What is the procedure? What is the methodology? How do we add more commands, more functionality to our computer? And by doing this, we're actually going to learn how to build a computer, because adding to a computer is the same as if a computer starts with nothing, and then you start adding. So by learning how to add to what is existing, we also get an inkling on how we could create a computer, or a better understanding of how we can create a computer. So all the diagrams that we saw up till now were basic diagrams. Some of them had a little bit more detail than others, but none of them had support for all the commands. We're going to learn how to give more support. Now, when we want to add a new command, which we're going to do, we're going to give two examples of commands that we want to add. And when we want to add a new command, we're going to have to describe a few things. We're going to have to describe what hardware we need to add, because maybe we don't need any hardware. Maybe the hardware and the chip is sufficient to do this. We just need to add some wires. But we may need to add an actual hardware element. And we're permitted to add any hardware element that we can imagine that could be built with logic gates. And we don't have to explain its inner workings. For example, if we have like a sign extension unit, we can just say we have something that does a sign extension. We can view it as a black box. We don't have to explain how it does its job, but we have to explain what it does do. 2, we have to explain what all the values on the control lines are going to be for that new hardware in all of the stages or cycles for executing our new command, and what changes there might be theoretically to other control lines for our command. In other words, let's look at this picture here. We have our controller, and he has control lines. If we add some new hardware over here or over here, we may need to add another line to control it. So we may have to add a new control line. We're going to have to explain what values should be on that control line for all 5 stages if it's a multi-cycle, or for all 5 steps, for all 5 cycles if it's multi-cycle, and for all 5 stages if it's a single cycle. But really, in a single cycle, the line is just going to have, we're not going to have to talk about stages. We're just going to have to talk about what the value of the line will be for our command if it's a single cycle. In a multi-cycle, we'd have to explain in each and every step what will be the new value in that line. Again, if we add a line, we have to explain what the values are, just like we know what the values are for these lines for every stage, if it's single cycle for the one stage, and if it's multi-cycle for all the stages. Okay, that's what he means, or that's what I mean when I say what values are on the lines for doing my new command. Also, we need to write what output will be created by the new components in each cycle. If we're talking single cycle, we just need to talk about one output. But if there's some new piece here, if it's 5 cycles, then there's going to be 5 different outputs. Maybe some of them are irrelevant, but we need to explain what they're going to be in each cycle. Or when they're relevant and when they're not relevant, we need to say. In the examples that we're going to do today, they're all going to be single cycle, so it makes our life easier. We don't have to explain in every cycle what the output will be. Fourth and finally, we have to explain what will be the values on the new control lines when executing other commands. In other words, I've again added some hardware over here, and there's a new control line. What is the value going to be on that control line when I'm doing another command, not the command that I'm trying to implement? Okay, so those are the 4 theoretical things we have to cover for each new hardware or each new support we provide for each new command. So here's our first example. We're going to jump right into some examples. And this is very similar to homework number 3, where we ask you to add additional functionality to the MIPS processor. Some of that functionality in the homework is theoretical. It's just like we made up some command. Some of it is real. The two examples that we're going to do here are real commands, and I can show you that they're real commands by going over here and showing you that there are. Here is the MIPS instruction reference, and if I go down to LUI, here it is. I see that there is a command called LUI, load upper immediate. What it does is it takes the immediate 16-bit value and puts it into this register that is specified by T. Now, look at the encoding here. It's important to understand. The first 6 bits here are the opcode. That just tells you that it's a LUI command. Remember, this is of type I, so I know what type it is already by the opcode. Now, the immediate value is the 16 bits over here, these I's. That's why it starts with an I, because for the word immediate. Now, all these are the bits of the immediate value, which is 16 bits, which means it could be the number 0000001, which would be 1, or it could be 2 or 3, up to plus or minus 32,000, approximately. And this, what's this T? This T is the 5 bits that specify which register I want to put this value into. Notice that these ones are blank because I don't need another register. I just need to take a value and put it into a register. Why did they choose to put it into the second register? We'll see later. But for now, just understand that the first register is always RS. The second register is always RT. So it's DAFCA, it's precisely the RT that is going to get the value. Now, this is not a load immediate. This is a load upper immediate. What does upper mean? Upper means the left-hand side, the upper values of the register. So normally I would put these 16, if it would be an LI, I would put these 16, just to load a value, would put these 16 bits into the right-hand side of the 32-bit register specified by T. But in this case, I'm going to put it into the right side and then shift it left, inserting zeros on the right side so that these I's, all these ones and zeros, will actually be sitting on the leftmost side, the left 16 bits, not the right 16 bits. That's why it's called upper. It's the upper half of the register. We'll get these values. And that, of course, will give it a lot larger value. If I put the value, for example, 1 in here, and I look at this register afterward, it won't be 1. It'll be 64,000. 64 or 32,000. It'll be 2 to the 16th. Anyway, it'll be a much larger number. So, because this 1 will actually have a lot of zeros after it. It'll have 15 zeros in front of it, because that's what I wrote here, 15 zeros and then a 1. But it'll have 16 zeros after it, as opposed to it being on the right side where it would just be 1 with no zeros after it. So that's what load upper does. It puts this value into the left side. So now that we've got that clear, let's go back to our slide, and let's see it written in black and white in English. First of all, it says, check that the LUI command, which I sometimes call LUI, cannot be executed in the current single cycle. That's the first thing we got to do. And then explain what changes must be made to allow for the LUI or LUI command. First of all, for A, it says, in the diagram of the single cycle, there is clearly no way to perform this instruction. Well, he just says that. Why? So if you look at it, there's nothing here that would provide me with this concept of moving something 16 bits to the left. I have a sign extender, but that does something else. That puts on the left side ones or zeros. But here we want to take the value and put it on the left side. So, and put zeros on the right. We don't have anything that does that. And there's no clear way to do that with what we've got. So that answers this question. What check that can it be executed in the current single cycle? No. Again, we're in single cycle. I put that in bold. We're in single cycle. We're not in multi-cycle. So, fine. Also here, the solution. LUI is an I-type command. Its format is, so we just saw that in the thing. It's I-type. And notice he writes RT, not RS, because RS is the first one. It's the second one, and that's what gets the value. The command is supposed to move the 16-bit of the immediate number into the most significant bit positions of registers RT, and put zeros in the least significant bit position. Okay, so we understood that. That's what I explained already. Okay, so now next, so here's that. Here we see that there's no way to do it. That's our single cycle diagram because we're talking about single cycle. And now solution continued. Required physical changes. 1, we will add a unit that we will call zero extend swap. You can look up on the internet why we call it that. Let's put a period there. This unit will take a 16-bit number and append 16 zeros to the right side, in the least significant bit positions, to produce a 32-bit result. So you see 16 bits go in, 32 bits come out. That is our 32-bit value. That is our 32-bit value, which has been shifted 16 places. Okay, how does that work? We don't care. We're treating it as a black box. That's what we said in the instructions, that you can add any hardware that you want without explaining how it works internally, but you have to explain what its inputs and what its outputs are, and how it plays, what role it plays in the design of the computer, and how it interacts with the other hardware. Now we are on to a multiplexer. A multiplexer which we're going to expand. But before I explain this, it's helpful to look at the diagram of the final thing that we're going to make. Here is the same diagram that we saw before, but we've added, more or less the same, but we've added a zero extend swap. That's that new piece of hardware. Notice it says 16 goes in, 32 goes out. That's our zero extend swap. And where does it go to? Well, first of all, let's ask a more basic question, or a primary question. Where does it come from? These 16 bits are the instruction 0 to 15. In other words, the instruction is sucked here out of the memory. It goes down these lines. Some of it goes up here, some of it goes down here. And the 15 to 0, which is the immediate value, goes over here. That was the way it was originally. If we want to confirm that, we can go back to the diagram here and see that, yes, indeed, those 15 bits went to the sign extender and also went directly to the ALU controller, or at least 6 of them went there for the function code if it's an R type. But in any case, all this is in our new diagram here. Here's the 6 bits going to ALU controller. Here's the sign extension. But along the way, we've siphoned off some of those bits. They've continued going there, but we've spliced in additional lines so that they not only go here, they also go here. It's like if you would have an extension cord or a light bulb at the end of an electric wire, and you want to put another light bulb, you just cut into the wire and add 2 more wires and connect your light bulb. And they have 2 light bulbs on it. So we've connected some more wires to these wires, and we've taken those same 16 lines and put them into our zero extend swap and produced 32 bits. So that came directly from the instruction. Now, where does it go? It goes all the way down to this multiplexer. And as long as on these control lines we choose the right number, in this case it goes up to 2, so we've got to choose 2. Let's say we did choose 2, then down this line will go the value that we've produced here. Now, where do we want that value to go? We want it to go to a register. So it's going to go straight into our register file, into the right data position. Now, you may say, well, is this a new line? Was that line there before? Is this multiplexer new? So let's compare. Let's quickly go back and look at the other picture. We see that there was a multiplexer here, and it did have a line going straight up to the right data. What did we do different? We took this multiplexer that has 2 things going into it and 1 coming out, and we made it into 3 things coming into it. So we've just expanded that multiplexer, and we've also added a control line. Here there's a control line because we only have 2 choices. That means either 1 or 0. So we only need 1 bit to control it. But if we're going to have 3 options, we need a whole other bit to choose that 3rd option. In other words, 1 will be this, 0 will be this, and 2 will be this new line. So we got to choose which line we want to pass through. So we're going to have a new control line and a new entrance to the multiplexer. And that's exactly what we see here in this diagram. 3 lines going in and 1 line coming out and 2 lines controlling it. This is the old line. We call it S0 because 0 is the first one. That's the one that was there. And now we're adding a more significant bit, S1. We're adding, and we're calling it by the name LUI, since it actually, that's its purpose, is to control the LUI functionality of our computer. We could give it any name we wanted, but we'll call it LUI. And notice where it comes from the controller. So that's a new control line that we've added. This is a new piece of hardware that we added, and this is a new multiplexer. Now notice it says multiplexer. We've removed also the old multiplexer. Notice that this multiplexer says 4 to 1. Why does it say 4 to 1? It's only 3 to 1. Well, the answer is that multiplexers only come in multiples of 2. So you can have a 2 to 1, you can have a 4 to 1, you can have an 8 to 1. Not even multiples of 2, powers of 2. You can have 8 to 1, 16 to 1. So the smallest one that we could get that would service our needs, that would have 3 entrances, is a 4-entrance one. Where's the 4th entrance? Well, he just didn't draw it here. No need to draw it. You could draw it. Well, in the other, we're going to see now that you could draw it with like an X going from it, like no connection, just an arrow going in with no connection to on the left side of the arrow. Okay, so now we understand the basic thing that we're going to do. Now, that's it. We just tell the control line to put this thing through and to come around. Now, but we're going to have to explain it more in detail. So here we are. Here we explained this black box, and now we're explaining the multiplexer, the new multiplexer that used to be 2 and now is 4. And notice he writes 0, 1, 2, 3, and by 3 we just write nothing. Theoretically, I could put an arrow here with an X or something with no bit, nothing, with 0 bits on it. But essentially, they just didn't connect anything here. It's like I have an open place to put a wire in, and I just didn't put the wire in. So notice it says existing. These are the ALU. Those are the 2 lines. I don't really care about them, but those are the 2 lines that were already there. They're still coming in. They're still doing their work. And the multiplexer will choose them sometimes. And here is my new 0 extend swap 32 bits coming in. And he's going to go through and come out. When will he go through and come out? When I choose 2. How will I choose 2? Well, S0 will be 0, but S1 will be 1. So it'll be 1, 0. 1, 0, of course, is 2, the value 2. So the new line, when it's a 1, and the old line, when it's a 0, that means that I've chosen my new command. Okay, this I just explained already to you, so we can go on. So here we are explaining the actual, now we're in more detail, even more detail. We're going to make a little table. If the old line, S0 is 0, and the new line is 0, then it does whatever it did with 0 before, ALU result. And if the old line is 1, and this is 1, it does whatever it did before. But if the new line is not 0, but it's 1, then basically, if the old line is 0, 0 extend swap data will be passed through. What about if it's 1 and 1? We're not going to allow that possibility. The controller will never produce those outputs. The controller will never send 1, 1 to those 2 bits, those 2 lines. Okay. Now so we've explained how it works. We saw the diagram, but we still have one more thing to explain, and that is all the lines, because I can't just explain what is my new line, LUI, new is 1. That's how we're going to get what we want. I also have to write that that's the S1. Where's the S0? That's the S0 is, look here, S0 is also called memory read. No, it's not called, memory read. So the memory read, he writes an X here. Because basically, really, it doesn't matter what's on this line. Theoretically, it could be a 1. As long as this is a 1, then sorry, I don't care. I'm looking at the wrong place. I meant this line. The S0 is the memory 2 register. That makes more sense. Memory 2. Does the memory go to the register? So that is going to be 0. No, it doesn't. So that's the 0 on that line. So when we're doing our command, we're going to have a 0 on that line. Basically, we're going to have a 0 on everything except for two places. On the LUI, we see a 1 there, and on the register write. Now, why is that very important? Well, obviously we need a 1 on the LUI because that's what's going to choose that's going to choose to pass on our new command, our new data. But also we need to have that data comes into the register file and gets written. If this register write would be 0, that would effectively lock the register file. That would mean the register file is locked up. Nobody can write to it. So I have to write it as a 1 to say, no, we're going to enable writing to the register file so that this data will actually get written. So those are the things I need to do. Now, why everything else is 0? We can go through one by one and see why it has to be 0. Why does branch have to be 0? Because I don't want to do a branch, so I want to put a 0 on this AND line, and that will automatically produce a 0 over here, which means it'll take the 0 of this multiplexer, which is coming from where? The PC plus 4. Well, that's exactly what I want. I want the PC plus 4 to come out and to go all the way around back into the PC. So that's why that has to be a 0. Why does the memory to read, the memory to register, well, that we explained. That's here. What about the ALU operation? Well, here it says XX. Why? Because I don't care what this ALU is sitting there, and he's going to do something. He's going to add or subtract. Every time there's a cycle, the ALU produces a result. But that result is going to go into this memory data, and it's also going to go into this multiplexer. Well, I don't care that it goes to this multiplexer because I'm not choosing it. I'm going to choose this other data. So I don't care. Whatever garbage this ALU produces, let it come into this multiplexer. It doesn't bother me. But, so therefore, I don't care. That's why there's an XX on the ALU controller. It doesn't matter what he does. I'm not using that result. But wait a second. It also goes into this memory data, and we could have a big problem. If it goes into the memory data, it might write to some crazy place in data memory, some garbage result. So therefore, I've got to lock up the data memory. How do I do that? Simply by putting a 0 on memory write. See memory write 0? That means don't write to the memory 0. Do not enable the memory write. As far as memory read, it says an X here. You see that memory read with an X? That's here. It doesn't really matter, although theoretically it should be true. We should read. And then, in other words, we can't have both of them 0. I think the rule is that on data, one of them is 0 and one of them is 1. So I don't know why I wrote X here, but basically it doesn't matter what it is, because even if we have a 1 there and we do read, which would be even worse than a 0, so what? We read and it comes out on this line into this multiplexer again. But again, we're not choosing 0 or 1. We're choosing 2. So it doesn't matter that that data came into the multiplexer. We don't mind that it comes in. So we can allow a read here, because anyway, what's going to go out is the result of our 0 extend swap. So, and what else? One more I didn't explain, which is the ALU source I didn't explain, but that's also for the same reason. I don't care about the ALU. But also this one, the register destination 0. This one has to be 0. Why? Where does it go? Down here. Goes to this multiplexer. Why does it have to be 0? This is very important. Because up till now we explained that the data came into this write data section. Fine, it gets written to this data. And it's enabled. But where is it going to get written? We didn't say where to write it. We just put the data here. But we have to choose one of the 32 registers to write to. Well, that's obviously, as we remember from the command, just a second, that is the not the RS, not the first one, but the second one, the second set of bits to specify a register. That's the RT. So that's what we've got to put it to. So let's see if we do that. Well, this is the opcode, 26 to 31. 21 to 25 is the RS, and 16 to 20 is the RT. And it even says RT there. Now the RT goes to read register. Well, we're not doing reading, we're writing. But it also comes down to this multiplexer. Well, if this multiplexer passes those 5 bits of data to this write register, it'll tell me which register to write to. Those 5 bits will tell me which of the 32 registers to write to. So that means I better have a 0 on this multiplexer. And that's exactly what I did. Register destination is 0. In other words, the register destination is coming from the RT and not from the RD. So that's excellent. Now we understand why, if we go back to the original question we asked this question, why is it that the RT is chosen and not the RS? We could have put the T's over here and put this immediate value into the RS and put blanks here and just use the RS. Why did we choose the RT? Now we are prepared to answer that question with the knowledge that we have now, which is that there is a line, there already was, in the diagram, a line connecting the RT directly to the right register. In fact, that's why it's called the RT, because T stands for target. It's like an alternate target. It's a target. It's a possible target. In other words, the right register can either come from the RT or the RD. If we would have put it in the RS, there's no connection from the RS to the right register. We'd have to draw a new line to this multiplexer and increase the size of this multiplexer so that it could also choose the RS. By the way, that would be an interesting question on the exam. How would you, a very simple question, how would you enable writing information to the RS? What would you have to do? And the answer would be very simple. You'd have to just have a line going down into this multiplexer. And you'd have to expand this multiplexer to 4. And then he could choose anyone. He could choose the RS, the RT, or the RD to write to. As it is now, though, the RT and the RD are the ones to choose. So it's much simpler to use the hardware that already exists. So that's why we chose the RT. Okay, so I've explained now why these are all the symbols why these are all the values that have to be on these control lines to do the LUI command. And that's what's written here in this table. Notice the 1, write data to the RF. We obviously want to write data to the register file, and the new command. In all other instructions, the LUI line will be 0. Remember, that was one of the things we had to do in our requirements. Explain what the LUI line will be, what our new control line will be for other commands. So the answer is it'll be 0 for all other commands. Nice. So we've seen this diagram. Hopefully now we understand it. We've added this. We've expanded this, and we've added a new control line, this big control line, and we've explained that. Wonderful. One last thing, we have to go through each stage. When are these things done? In which stage? It's kind of more interesting if it would be multi-cycle to explain this, but we've got to explain it also in the single cycle to explain what happens. Now, remember we said that the stage 1 and 2 are identical in all instructions. So to our command will be identical. In stages 1 and 2, we don't even know what the command is. Now, by the way, what is the meaning of stages? Just as long as we're talking about this, what does it mean that there's stages? If it's all one cycle, it all happens in one cycle. Why do we divide it in stages? Because even though it's one cycle, it takes a certain amount of time for the electricity to reach where it needs to go. And by stage 1 and 2, the electricity has reached these points, but it hasn't yet reached some other places. That's the point. So in stage 1 and 2, we do all the things we do for every command. I'm not going to explain what those are, but remember, I can explain it. It's just increasing the PC by 4. It's computing the branch address if we need, for just in case. A few other things. So that's what happens in 1. It's reading the instruction. By stage 3, we already know what the instruction is, and we know it's a 0 extend swap. And our 0 extend swap, it's a LUI. Our 0 extend swap is going to produce this 32-bit result. It's going to take the immediate value and append. These two lines mean append. It's going to append 16 zeros to the right, and that's our final result. And that line and since the controller knows that it's an LUI command, the control line LUI will be set to 1, which is S1. And memory to reg will be 0, so that we don't write to the, so that's how we choose on the multi, we say no, do not write the memory to the register. So that's a 0. That's the S0. That's the S0 line. Those are the two lines that control the multiplexer that we talked about so much. And that will cause the multiplexer to select the result created by the 0 extend swap, as we explained. In other words, that's what we're choosing here, S1 and 1, S1, S0 and S1, and the value is going to go through. That's what we explained, here. So that's what happens in stage 3. And now the data has come, and we have to wait for that data to reach the register file. And now we're prepared to write it in the register file, which is going to take a little bit more time electrically. So that's why it's stage 4. The selected data that we chose from that multiplexer will pass from the multiplexer output to the write data lines of the register file, as I explained. The control line register destination is set to 0. That's over here, set to 0. This control line is set to 0, so that the multiplexer will choose the RT to go to the register, and not the RD, which is irrelevant here. Causes the multiplexer to pass the RT value from the instruction to the write register of the register file. The register write will be set to 1 so that I can actually write to the register file, otherwise it will be not enabled. And that will cause the LUI data to be written to the selected register, i.e. the register indicated by the RT. So we've written our data to the RT. Anything else to do? No. We have finished the command in 4 steps, in 4 stages of the single cycle. All right, so we have seen, basically I just wrote down here what you'd have to write in your homework. You can't just draw a picture. You got to explain why each piece is there and what it does. And that's what I've done here in English. Okay, now a second example, and that would be even a simpler example, supporting the jump command in a single cycle. So in this diagram, we have seen diagrams, some of them, like I said, were more full and some of them were less full. But in this diagram, we don't see any support for a jump. In order to do a jump, remember, you need 26 bits from the instruction going all the way to the PC. So that will be the new PC, plus some more bits. But 26, the instructions, I don't see any line here that has 26 bits going anywhere. The most I have is the 0 to 15 bits going here, but that's not 26 bits. That's not what I need. So clearly, I cannot do a jump in this diagram. Okay, now that we've established that the jump that we've seen we need to do doesn't have a way of being done in the chip in the most basic diagram, we are going to need to add some hardware to the chip so that we can accomplish our jump properly. Now, you look here at number 1, it says we will add a shift left 2 to shift the target address 2 places. So remember, one of the things we have to do is take those 26 bits and move them to the left 2 spaces. So we're going to invent a machine or a piece of hardware we're going to call the shift left 2, which does precisely that. It moves a 26-bit input and moves it left 2 spaces and produces a 28-bit output with 2 zeros at the end. The unit, we're going to call it shift left 2B, actually, because there might be another one in there. And it will do just as I said. And we're going to then have to add to it 4 more lines from the PC, plus 4. And there's the PC. We're going to take 4 lines from it and add it to the 28 bits that we've got from our shift left 2 and getting a total of 32 lines, which will be a 32-bit address. So let's see. First of all, let's see the description of this new piece that we're adding. Notice here it says diagram of the jump hardware. So it says shift left 2 and give it a name B. And instruction from, you see it says 26 instruction. That means from the instruction, from the actual instruction that we wrote in code, which was 32 bits of instructions, though the 26 bits of it from 0 to 25, which is everything but the opcode, we're going to send into this shift left 2. Why are we doing that? Because that's exactly where the address in the jump is stored. And out is going to come 28 bits, which is that same 26 bits with 2 zeros. But that's not a full-size address. We need a 32-bit address. So on the right here, you see coming in 4 more bits are joining up with the 28 bits to produce 32 lines, electrical lines, or 32 bits. You can think of it as like a highway, some kind of very broad highway with, let's say, you may have been on a highway, there's 4 lanes, and then another 4 lanes come in, and they don't merge, they just run parallel. Now it's an 8-lane highway. So these 4 lines are not merging in, but they're just adding on. So what was a 28-bit, 28-line highway is now going to be a 32-line highway because 4 lines came in from where? From the PC after plus 4. What does it mean, PC plus 4? It means after we incremented the PC. Because remember, each time in cycle 1, or in stage 1, if it's single cycle, we increment already the PC 4 places. So those are, and we take which bits of the PC? We take bits. We don't take the whole PC because then we'd have 28 and 32. We'd have 50 lines, 60 lines. We don't want 60 lines. We want 32 lines. So we only take 4 lines from here. Which 4 lines? 28, 29, 30, and 31. That's what that means, 31 to 28. And we get our 32-bit jump address. Now, let's go ahead. These are the control lines. Let's look at it first in the diagram. Here we see the diagram, and we've added this line here. The instruction, here's the instruction, and it gave us 32 bits. Then some of those 32 bits went to various places. Went to the RS, the RT, the RD. The last 15 went to the sign extender and also to the ALU controller, the last 5 of them. In general, we've already sent the data somewhere, but we can add another line, splice in to our electrical lines 28 connectors to these 32. We connect 26 connectors. 26 lines are going to go up, 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 and go into our shift left 2B. Notice why do we call it shift left 2B? Because there's already a shift left 2 over here. That's obviously shift left 2A. We're using that for a branch command. But over here in our jump command, we're taking our 32-bit and we're putting it into this machinery, and we're getting out our 28 bits. And notice that's 28 bits, but then it becomes 32, 0 to 31. The jump address continues on here. How did it become 32? Because another 4 lines, see that little 4 there? That means 4 lines came in and went in parallel. Now, where are those 4 lines coming from? They're coming from the PC plus 4. How do I know that? Well, right here, look. The PC went into this adder, 4 got added to it, and it produced whatever the PC was plus 4. And all those lines come out and they go in over here for eventually to go back to the PC to increment it. But we're going to siphon off 4 lines. Now, all 32 bits, all 32 lines continue here, but 4 of them also continue up here. And that is going to add to our jump address so that we get 32 lines for our jump address. And that's exactly the hardware we're adding. We're adding this line, we're adding this line, and that's all permitted because we're just adding more lines. The same electricity will go multiple places now. Now, where is it going? That is an interesting question. It is going, you see, if it would go directly after here to the PC, that's where we want it to go, right? We want to increment the PC, not to plus 4, but to whatever the jump address is, so that when the next time we want to take a command from memory, we'll take wherever we jump to, that command. So we need to increment the PC to tell the memory which command to take. So we really should put the line directly into the PC. But if we would do that, then no matter what the command would be, we would always be doing a jump. We'd always be doing some kind of jump because we'd always be taking these numbers and putting them through. We don't want to do it unless the opcode is 004 or 001111, which is the opcode for a jump. So we need to check the opcode over here, and then what we need to do is we need to not just send it directly, but notice this line, it's hard to see a little bit because there's so many lines here, but it's coming all the way to this E multiplexer. E is just the letter we gave it. This multiplexer over here. And what this multiplexer is doing is saying if the control line here on top is 1, then send along the jump command to the PC. But if this control line is 0, then send something else. And we're not concerned right now with what else it is, but something else. The correct, could be the PC plus 4. But send something else. So this is like a last stage multiplexer to decide whether we're going to send the jump command or not. And so we have to add this new control line on our new, we've essentially added a multiplexer here. In other words, we've added this, we've added these two lines, and we've also added a multiplexer. And if we've added a multiplexer, we've got to add a new control line, and it comes all the way down here. And what name do we give it? Well, we call it jump, because it's the multiplexer that controls whether we're doing a jump or not. Of course, we could call it, any name we wanted to, but we usually give it names to define what its purpose is. So this is the jump controller. And if it's 1, that's what that means, a 1 there. If it's a 1, then that means choose 1, choose the jump. When there's 1 is true, so if it's truly a jump, then we're going to send a 1 over here, it means it is a jump. And then it's going to get a 1 over here, and it's going to choose not the 0 down here, but the 1 up here. And that means this data will be allowed to pass through the multiplexer and not the whatever data came over here. And that's our jump. And any other time, if it's not a jump command, we'll simply set jump to 0, which means it'll choose this and it won't choose. So we'll have done our calculations for a jump over here. We'll have created a nice address, but we're going to not let it pass on to the PC. It'll reach a brick wall and not continue further because it isn't a jump command. In other words, our calculation here is just gibberish, is meaningless. We took some bits and we calculated something, but it wasn't a jump command, so this address is a meaningless address. So therefore, we're going to close it off if it's not a jump command. So therefore, we have complete control. The controller reads the opcode. It gets the instructions 31 to 36. It gets the opcode and decides if it's a jump. It lights up this. But we also have to explain what other control lines should be lit up or turned off. And you notice here it's written here. X means that it's a don't care. We don't care what's there. Could be 0, could be 1. Either way, it'll work. But some of them are zeros, which means it has to be 0. So what's a 0? Notice that it says memory write is 0. Well, that's very important because that's very important because that line is going all the way to the memory. And that's saying this is the write enable entrance. This is the read enable entrance. Or this is actually, this is the read enable entrance. So that read address is referring to this arrow. But this is the read enable and write enable. We want the write enable to be 0 because otherwise the ALU, you see it's sitting there and some value is coming in here no matter what we do. Something is being read by this, whatever, it's maybe meaningless, it's maybe garbage, but something is being read and it's going to the ALU and the ALU is doing some kind of addition or subtraction, something, and the result is going to go into this memory. And it's going to write to some place that's going to be determined by whatever this is. So we're in trouble, kind of. So it's going to write whatever this data is, whatever came out of this line. So we're going to be writing to some data, which we don't mean to be doing because it's a jump command after all. Jump is not supposed to write to data. We don't want that kind of side effect. We don't want also to write to a data and also jump. We're just doing a jump. So therefore, since it's automatically, this hardware is there, we need to build some brick walls. We need to prevent the data from getting into the memory. How do we do that? Simple. We have this control line, which is called write enable. If we put it to 0, which is what we did here, memory write is 0. That means 0, false. You're not allowed. It's locked. It's not enabled. So we are unenabling this. So that means no matter what data tries to get in, the door is locked. It won't get written. The data maybe will come in, but it won't get written anywhere. So therefore, whatever value comes out of here, I don't care what it is because I know I've locked it up. I've locked up this. And therefore, the ALU, whatever it calculates, is irrelevant to me. Therefore, whatever values the ALU controller gets, which controls what the ALU does, is also irrelevant because no matter what it does, if it does minus or addition, no matter what it does, it won't get written. So therefore, I put an XX on the ALU operation here. In other words, the ALU operation is a don't care. There's these two lines, both of them are X. Everything else is going to be X too. Like, for example, the branch. I don't care whether it is a branch or isn't a branch, because whatever value I put here, it's going to be ignored, because the only value that's going to get by this last multiplexer is the jump. Whatever I calculated over here is irrelevant. So these lines are all don't cares, except for one more, which is the register write. Also, it's a write. Just like this was a memory write, this is a register write. And this 0 is going to tell me, don't write anything to any register, because this is the register file. If he gets a 1 here, he's going to write whatever data is on this line, and there's going to be some kind of garbage data on that line. He's going to write it to whatever data is on this line. So we don't want to accidentally or unintentionally write to some register, so we better lock the register file. So the main things to understand here is that the 0 and the 0 here need to be. Everything else is a don't care, because it's irrelevant, because I've basically accomplished everything that I need over here. I don't need any of these other parts. The 32 comes in, the shift, and it's done, and I've done it. So everything else I don't care about. I just want to make sure I don't, by accident, write something over here. So now I've explained to you all the control lines, what they're supposed to be, and why some of them are don't care. And that's what's written over here. This is the way you should write it in your homework. In other words, well, this should be, no, there's a typo there, or it's a spell correct that didn't like when I wrote op, so change it to or, but it should be ALU operation. 2 lines, irrelevant. Anyway, everything is irrelevant except for the memory write, the register write, and obviously the jump has to be 1. That's our new command. 1 to choose jump address, 0 for all other instructions. That's a key line, because we said that we have to specify what will our new line be when it's not a jump command. So it'll be 0. That's usually what it's going to be. That's our diagram we saw. That's our table. That's our hardware. We don't have to explain the multiplexer that we added, because everybody knows what a multiplexer is. And now we just are left with the last slide for this lecture, and that is the actions carried out for the jump per stage of execution. In other words, even though it's single cycle, we can talk about what happens first, second, third, because the electricity takes some time to travel. Now, notice that stage 1 and 2 are identical to all instructions, because all instructions are going to be identical, 1 and 2. If you remember what 1 and 2 does, it calculates a branch address, and it also increments the PC by 4. All that stuff is going to happen anyway. But in stage 3, we're going to take the 26 bits of the target address from the instruction, and we're going to pass them to that shift left 2B that we created, that we added. And that's going to give us 28 bits, which means it's going to put zeros at the end. And then it's going to take the 4 most significant bits of the PC plus 4. In other words, the PC already incremented. And it's going to take those 4 bits, those 4 lines, and prepend them to the 28 bits. In other words, put them at the most significant bit location. And then it'll produce a 32-bit address. And we can write that mathematically, and we can say the 4 most significant bits of the PC after incrementation, plus 4, right, after incrementation, plus the 26 bits from the instruction itself that was written in the instruction, plus, appended to that, this is append, this plus means append. Appended to that, we cut and paste on the end 2 zeros. So we've got 2 zeros, 26 bits, and then prepended these 4 most significant bits of the PC. This address is then passed to the right multiplexer, which we called E. That's just this one. It's always good to label them with letters, because then you can refer to them in your notes by those letters. Control line jump equals 1. Well, that's what we said. That's our new line. Causes this multiplexer, MUX is short for multiplexer, to choose this address and to pass onto the PC register so that the address for the next instruction will be changed to the jump address. Well, that's exactly what we're saying over here. It will go here all the way down here to this PC register. Now, why is it a register? Well, because it needs to store the data for the next cycle. Anytime you need to store data between one cycle to the next, since it's a single cycle, the next command The next cycle will be a whole new command, and we'll have to get the value in this register. It's after a whole clock cycle, so therefore we need to use a register to store it. So there we've explained how to do jump, how to add jump to our existing basic MIPS diagram. For the homework number 3, you have to add, I think, 4 new commands. There's 4 different questions to the diagram. And you can simply take a diagram that's sort of a basic one and write and then add to it. Just cut and paste the picture and then add to it. And then you're going to have to make these charts of what the lines are going to be. And you have to answer these questions. Remember we said at the beginning, what are what hardware I need to add, what will be the value of the control lines, what will be the output by the new component, and what will be the values on the new control lines when it's not executing. That was the 0 if it's a jump. If it's not a jump, I mean. So that's it for today. Next lecture will be chapter 7. Good luck.